So this chapter is about polynomials. Even though we took a day at the beginning to review properties of exponents, it's still mostly about polynomials. And when we say polynomial functions, then it basically it's not just that we're going to introduce what we mean by polynomials, but we're going to be talking about graphs. And if you look in the book, the way they've got the first section, 5.2, after the properties of exponents, there is a little bit about graphs. But most of the stuff about graphs is at the end in 5.8. So it's a combination of the two. Now, if you look at these objectives here, classifying polynomials by degree and number of terms, identify domain, range, intervals of increasing and decreasing, and end behavior of a polynomial, right? Use zeros and end behavior to sketch the graph of a polynomial function. Understand the maximum number of turning points. Some of this stuff is like directly addressed by the book, and some of it is not exactly. And we're going to talk about all of it, but the homework in the end is going to be about the things that the book has got. But I'm trying to integrate as we go along all the things about functions like domain and range and intervals of increasing and decreasing. Those things for sure are not really addressed specifically, but we'll do it as we go along. But definitely end behavior, that was one of the things you copied for the extra credit homework about the end behavior, which we've talked about a little bit before. So let's do this. So polynomial literally means many terms. Okay. Monomial, mono stands for one term. Binomial, 2 terms. Trinomial, 3 terms. Okay? And above, 4 terms and above, usually what we say is polynomial. Now, truthfully, they're all polynomials. Everything can be considered a polynomial. But the definition of a polynomial is it's the sum of monomials, so it's a sum of terms. All the exponents have to be whole numbers. All the coefficients have to be real numbers. So the first kind of problems we do is just basically, say whether something's a polynomial by looking at those 2 things. The thing about polynomials are that we know that their graphs are smooth and continuous, right? They have graphs that you could draw without picking up your pen or your pencil, and they don't have any sharp corners on them like the absolute value v, right? Which is important when you get to calculus, and the first thing you do in calculus, it's called differentiation. Polynomials are everywhere differentiatable because they have smooth, continuous graphs. Okay. So we do a lot of work with polynomials. Okay, the degree of a polynomial means the highest exponent. So it's easier to see maybe starting at the bottom. But usually if you write a polynomial in standard form, it's got the highest power term all the way on the left, and then in decreasing order of the exponents. So you just have to look at the term all the way on the left to say, okay, like the last one, it's x to the 4th, so that's degree is 4. The cubic is x to the 3rd, degree is 3, right? The quadratic is 2, linear is 1, but even a constant, even if you just say y equals a constant, like y equals 1, that has a degree of 0, because, as we just did in properties of exponents, what is anything to the 0 power? It's just 1 anyways, right? So even though you don't see it there, you can say that it's x to the 0 power. So a constant has actually got a degree. The degree is 0. And the type, so when it says, what is the type, then we're looking for that, constant, linear, quadratic, cubic, quartic. Actually there's one above that. Quintic is 5. But I've never heard the terms for 6 and above. I imagine that there are some terms for 6 and above. Now, most of our work is like, we go a little bit into quartic and a lot more into cubic and quadratic. But when we get near the end of the course and we're doing these scatter plots, where you get a whole bunch of data and you have to enter them in the calculator and then you try to make a mathematical model out of them, you do that in the calculator. I'll show you at Stat, and you arrow over to the calc in the middle, and you can see in the menu there, starting at number 4, 4 is for linear, 5 is for quadratic, 6 is for cubic, and 7 is for quartic. And they don't go any higher than that. They only give us those 4 options. So we'll do the same thing. No point going above quartic if we don't actually have to go above quartic. And you can see actually there's another linear at 8. Then it's ln, that's a logarithm. Then it's exponential. Then there's combinations of logarithms. There's a sine, that's a trigonometric function. So you can do a whole bunch of really sophisticated modeling with your calculator. But the first ones we do, the first 4, they're all polynomials, up to quartic. And don't confuse quadratic with quartic, because they both start with QUA. Because a lot of times kids have to give the type, they give the wrong one, because they're confusing it with the other. So we have to decide whether this function is a polynomial function. Okay? So again, there's really only 2 criteria. Are the exponents whole numbers? Are the coefficients real? What would you say? How many say it's a polynomial? How many say it's not a polynomial? So it's a polynomial. Look at the powers of x are 1 and 2. So those are whole numbers. The coefficients are the square root of 3 and pi. And those are real. More than that, they're irrational. But it's okay to be irrational. I mean, the only ones they couldn't be, as far as we know so far, well, what's the only kind of number we know of now that's not a real number? Imaginary, right? So as long as they don't have eyes floating around, the coefficients will be okay. But if they had an eye in there, then we'd have to say, okay, that's not a polynomial. So now that we've said, okay, this is yes, this is a polynomial, then it says put it in standard form. So that's a yes for polynomial. Okay, standard form, you should put the highest power term on the left and then have it in decreasing order of the powers. So the highest degree term is pi x squared. And the next, plus 7x. And the next, minus the square root of 3. I mean, in the end, the square root of 3 is just a constant. Okay, now, what is the degree? That's the type. What is the degree? The degree is 2. The type is quadratic. And by leading coefficient, they mean what is the value of the coefficient of the highest power term. So since we wrote the highest power term all the way on the left, it's the leading coefficient. And it is, leading coefficient, C, is 7. No, sorry, pi. So the leading coefficient is pi. Okay, how about this one? Is it a polynomial? Why is it not a polynomial? Yeah, -1 is not a whole number, right? Negative numbers are not allowed. Again, if you had a negative exponent like that, it would not have a smooth, continuous graph. There would be some place, because what is, by properties of exponents, that's like 3 over x, which means you cannot let x equal 0. There's going to be a discontinuity in this graph when x equals 0. So it wouldn't be a smooth continuous graph, not a polynomial. This is no. So we don't have to do the rest of that stuff because it's not a polynomial. So here's your U-try. Is it a polynomial? Okay, so then you're done with that U-try. No, because of that. Okay, how about that one? Is it a polynomial? So write it in standard form, state the degree, type, and leading coefficient. Okay, the degree is 2. The type is quadratic. And the leading coefficient is 6. Positive 6, right? Okay. So the graphs of polynomial functions for the 4 that, I'm not including a constant. What would the graph of a constant function look like? It's a horizontal line, right? If it's y equals a constant, it's just a horizontal line. But a lot of what we're talking about here, we're really not interested in that one. So we're kind of starting at linear. So the standard equation for a linear equation is y equals mx plus b. In fact, in the calculator, they say y equals ax plus b. So let me go to quadratic. In the calculator, the y, well, actually what we did in class, y equals ax squared plus bx plus c. For cubic, y equals ax to the third plus bx squared plus cx plus d. Do you see the pattern? You're always starting with a, and then you just keep adding another letter at the end. So what would quartic be? Right. Right, that's the standard form. Okay, in all of those equations, where do you find the y-intercept? The y-intercept should be the constant term, right? Remember, the y-intercept is where x equals 0. And if you substitute x equals 0, all the terms except the constant term drop out. So you're always looking at the last term, that's the y-intercept. Okay, now you can see why in the calculator they call linear y equals ax plus b. Because that's just their general pattern, right? For quadratic it starts with an a, and cubic and quartic is always with an a. Okay, so we know that sometimes a straight line will go up and sometimes a straight line will go down, right? How do you know which, when is it that it goes up and when does it goes down? But what is it in the equation that's telling you that it should be? If the slope is positive, which is the a or m, right, then it goes up. If the slope is negative, then it goes down, right? So this is for, I'll use m because that's really what we're used to. M is greater than 0. This one is m is less than 0. Okay, the same thing. You could have a parabola that opens down. And we just did this, right? How do you know, what is it that tells you whether it opens up or down? Okay, what part of the equation tells you if it flips? The a, right? If a is greater than 0, then it opens up. If a is less than 0, then it opens down. Okay, well, the same thing is going to go for the cubic and the quartic. Did you have a question? Okay. The same thing will go for the cubic and the quartic. If a is greater than 0, if a is greater than 0, then it's like it is right there. But if you had a less than 0, then it would start high and end up low. Like that. And notice that, well, notice that for linear, it's the same thing. Linear, if m is greater than 0, then it starts low and ends high. And for cubic, if a is greater than 0, then it starts low and it ends high. Right? And the same goes for m less than 0, a less than 0. Right? For quartic, it could also be flipped. And as you might expect, the condition for flipping it is that a is less than 0. If the leading coefficient is less than 0, then it flips. If the leading coefficient is not less than 0, then it's opening up. And again, that's exactly like the parabola, right? The parabola opened up when a is greater than 0, and it opened down when a is less than 0. So even though we're only showing these 4, the truth is that these patterns hold for the higher exponents. So like for every odd exponent, if the leading coefficient is greater than 0, then it should start low and end high. Right? So if we did a fifth degree polynomial, a quintic, then it would have that same basic pattern. That's what you copied for that leading coefficient key concept block. Right? For if I went to the degree of 6, I would have more wiggles in between the ends of the arrows, but it would still, if a is greater than 0, it would essentially be opening up. And if a is less than 0, then it's opening down. So there's only two things that determine the end behavior of these things. And that is the degree odd or even? Is the leading coefficient positive or negative? If that's all you know, then you can determine the basic orientation. Where does it start? Where does it finish? Okay, so if the degree is odd and the leading coefficient is positive, then we would expect that it does something like this. And how do we say that? The end behavior, we would say I'll write it down here, as x approaches negative infinity, y approaches negative infinity. Right? You can see the left side of it there. I'm just kind of circling it. So as we're going to the left on the x-axis, the graph is going down. Right? As we go to the right, the graph is going up. As x approaches positive infinity, y approaches positive infinity. And you could get away without writing the plus. Just say as it approaches infinity. Okay. Oh, I went too far. Okay, if the degree is odd and the leading coefficient is negative, like the line with a negative slope, right? Then it's reversed. So we would say the end behavior as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches negative infinity. And you copied this in that block. Right? If the degree is even, and the leading coefficient is positive, that would be like a quadratic, which is opening up, right? So I can draw it like a quadratic. It just as well could be a quartic. Basically, it's doing the same thing on both sides. So I can just write with one statement, as x approaches plus or minus infinity to the left or to the right, y approaches positive infinity. And the last one would be, if the degree is even and the leading coefficient is negative, that would be like a parabola which is opening down. So, I mean, if you had one, like, so what if I threw one in here which is x to the 16th? Okay, all you care about is odd or even. That's even. So you don't have to draw a polynomial with all these wiggles in the middle. Just draw a quadratic. Just draw a parabola that opens down, because the end behavior will be exactly the same. Right? It's the same for all even degreed polynomials. So this would be more like this. So as x approaches plus or minus infinity, y approaches negative infinity. It's going down on both sides. That's all it's saying. Now, I want to skip ahead just to see. Okay, that's coming up. So based on that graph right there, do you think the degree is odd or even? If it starts and finishes in the same direction, which is it? It's like that one, right? It's finishing in both on both sides. It's going down to negative infinity. Therefore, it is even. So you would have to say this is even. And would you say that the leading coefficient is positive or negative? It's opening down, so it has to be negative. Okay, so do that one. Shouldn't take too long. Is the degree even or odd? Odd, right? And is the leading coefficient positive or negative? Yeah, again, since it's odd, then it should be similar to linear, because that's first power. That's also odd. And you know, if you looked at a straight line that had a negative slope, let me draw that. You know, it should have the same end behavior as whatever the odd degree polynomial is. So we're going to say negative. Odd and negative. Okay. So all the slides up to there are from 5.2, and they really there's homework problems that ask just those kinds of things. And I don't think you'll have any trouble with those. Okay, now this stuff that I'm going to talk about, domains and ranges, they actually don't ask you about that. But I just still want to make sure we're always talking about domains and range. So far we've done absolute value functions and quadratics. And what was the domain of both of them? All real numbers. And the fact is the domains of all polynomials are always all real numbers. That's why it has a smooth, continuous graph. Okay. Now ranges, not quite the same. For an odd degree function, like if you take linear, what do you think the range is of that line?
All real
It's all real numbers, right? The arrow's going infinitely up and infinitely down. Even if it was, let me undo that. Even if it was, let's say, a cubic. You know, they may do some wiggling around in the middle, but still the arrows go infinitely up and infinitely down. So it's all real numbers. And not only that, you know, as we saw with quadratics, it's possible that you have a parabola that doesn't cross the x-axis. But is it possible that you have an odd degree polynomial that doesn't cross the x-axis? I mean, if it goes infinitely down and infinitely up, is there any way that it doesn't hit the x-axis? No, there's no way. So we always know that odd degree polynomials, they have to have a real zero. They have to have a real zero. Even degree, you don't know, because since it opens up or down, if it's already above the middle or below the middle, it actually could miss the x-axis altogether. So now, as we saw with quadratics, the range of a quadratic function is not all real numbers, because it only goes down so far, and then it goes back up again. And that'll be the same no matter if it's a, you know, let's say it's a quartic that has this kind of a shape. You know, it definitely goes infinitely up because those arrows are pointing up, but it doesn't go infinitely down, right? It only goes down as far as the lowest part of the shape. So you always would have to say that the range is limited if it's an even degree polynomial, and you just have to kind of look at the graph to see what it is. You know, how far does it go down? It'll end up being some kind of a statement like y is greater than or equal to, pick the number, you know. Okay, so now this stuff here is coming from the 5.8. It's the graphs of polynomial functions. Some of which we've kind of done this stuff already. I mean, if you look, this was a similar, well, we had a test question that ended up, you had to solve, and you ended up with this kind of a thing. 0 equals x minus 2 times x minus 3. And we said then the solutions were 2 and 3. So we would say that if k is a zero of the function, then x minus k is a factor of the polynomial. Okay, well, you know, if 2 is the solution, then x minus 2 must have been the factor. Right? If 3 is the solution, then x minus 3 must have been the factor. So these things are really saying the same thing. Or it says that k is the solution to the equation f of x equals 0, which is what we've already got. Or it's another way you could say it. If it's the 0 of the function, then it's the x-intercept. And so the x-intercept is a point, right? So it's k comma 0. You know, these two, this 2 and 3, that means that these 2 points are on the graph. 2, 0 and 3, 0. Good. Interesting. So these graphs that we're going to do here, I call them a sketch because I really don't expect that they're like exact, but it's yet using the information that we've already covered today to just sketch out a graph, which is not bad. In the book, if you look at the examples for this, they actually go another step and make a table of values and get some more points to make it more exact. You don't have to do that for me. You don't need a table of values. I mean, I just want to say let's use let's use zeros, the y-intercept, and the end behavior that we understand now to sketch in the graph. Now, if you look at this one right here, it's not in standard form, but that's okay. We still should be able to tell what is the degree of this function. What would be the highest power of x if you did FOIL it? Well, let's see. The first factor, x plus 3, that's x to the first, right? And if I FOILed x minus 2 times x minus 2, what would that give me? An x squared. And then if you multiplied that by x to the first, you would get 3. Yeah, I mean, this is a multiply, right? You have to multiply those two together. So if I multiplied x minus 2 times x minus 2, I get x squared. And then if I multiply it again by x plus 3, I would get x to the third. Right? That's a 1, that's a 2, so the degree is 3, which is odd. So for end behavior, all we really care, is it even or is it odd? It's odd. Okay, is the leading coefficient positive or negative? It's 1/6, so it's going to be positive. So the leading coefficient, I'm just going to abbreviate LC. Leading coefficient is positive. So what does it tell us about the end behavior if it's odd degree and positive leading coefficient? Does it start here? It starts on the bottom, right? So definitely it's doing that kind of thing on the left side of the graph, and it's doing this kind of thing on the right side of the graph. So we just kind of have to know that. Okay, now what are the zeros of this thing? -3. Oh, darn it. I didn't realize what I was doing. I have to fix that. X plus 3. X minus 2 squared. Okay, so the zeros are in factored form. You should be able to just read them off, -3 and 2, which means there's going to be a point right there, and there's going to be a point right there. Okay, and then it says find the y-intercept. How do we find a y-intercept of a function? Say again? Put x equals 0, right? On the y-axis, x equals 0. So if you substitute x equals 0 and solve, you'll get it. Right? So I'll go 1/6 times 0 plus 3 times x minus 2. Sorry, 0 minus 2. 0 minus 2. Squared. And what's that going to be? The -2 squared will be 4 times 3 is 12 divided by 6 is 2. So we know that it has this point on it too. Okay, let me get rid of that. Okay, so we're trying to draw something that starts in third quadrant. It goes through the 0. It hits the y-intercept, and then somehow it's got to go through that 0 and end in the first quadrant. Does that look possible? It is possible, but this is a new thing that we're just kind of learning on this slide, which is whenever you see that your 0 comes from a factor which is squared, then that means that the graph is going to look like this. I mean, you remember when we were graphing perfect square trinomials? What did they do? They touched the axis and they went back on the same side. Why is that? Because, if you look around x equals 2, right at that spot, if you plug in 2, 2 minus 2 is 0. If I go a little bit to one side or the other and subtract from 2, or subtract 2, to the right I'll get a positive number and I'll square it. To the left, I'll get a negative number, and I'll square it. But in either case, it's the same sign. So it doesn't change sign when it gets to the 0. That's why it stays on the same side of the x-axis. Now, if it's to the first power, then that means it does cross the x-axis. It changes sign when it gets to the 0 and goes to the other side. So in this book, they call that behavior near zeros. Right? When the factor is raised to an odd power, not just 1, but any odd power, then the graph crosses the x-axis at x equals k. So, I mean, if it's to the third power, you know, you can take a negative number to an odd power. Basically, it will change sign because it's raised to an odd power. But if it's raised to an even power, like what we just saw in that last one, they say the graph is tangent to the x-axis. Now, you did this, you used tangents in geometry with circles, right? What did it mean to be tangent? It just touches at one spot and then it keeps going. Well, that's what they're saying about the x-axis, and when the factor is raised to an even power. It just touches and it goes back on the same side. Again, just like we saw with perfect square trinomials. Now, I mean, it could be like 2, 4, 6, 8. But the reality is, I mean, most of our problems, it's probably going to be squared. We don't often find one that's raised to the 4th power even, and certainly not to the 6th or anything higher. And even the odd powers, most of the time, it's 1. It's not even 3. It's just 1. But you got to keep those two in mind. Okay. I'm moving pretty fast. Let me see if that was the right side. Okay. So try to do the same thing with this one. Try to figure out where's your zeros, where's the y-intercept. Are the zeros going to have the tangents, or are they going to go right through the x-axis? What would the end behavior be? So again, in order to know the end behavior, you have to know what is the degree. Is it odd or even? And is the leading coefficient positive or negative? And so what do you say about the degree? Again, so the first factor is squared and the second factor is to the first, so it'll be cubed, right? It's to the 3rd power. So the degree is odd. The leading coefficient is positive. So what that tells us is doing that kind of thing again. What are the zeros? 1 and 4. And what is the y-intercept? Anybody? -8. I mean, it's -8. I mean, you know that the y-intercept is going to be the constant term, right? If I FOILed x minus 1 times x minus 1, what's the constant term? plus 1. Negative 1 times negative 1 is 1. Okay, then I multiply that positive 1 times negative 4, negative 4. Then I multiply the negative 4 by 2, negative 8. I mean, you could put this all in the calculator and do the calculation, but the answer is it's negative 8. Okay, and now, are we going to have any zeros that have the behavior near the zero that it's just tangent to the x-axis? Which one of those zeros is going to be the graph is tangent to the x-axis? Right, the one that comes from the factor, which is squared. So I'll draw all this in here, right? 1, 2, 3, 4, 5, 6, 7, 8. Negative 8, 1, 2, 3, 4. 0, 0, 1, and 4. And we know that at 1, it should like bounce off the x-axis and stay on the same side. So it should be doing this. It goes through the y-intercept, off of the 0, down to some degree, and then up again. Okay. Right. Try that one. What's going to be the degree of this one? You know, you've got x times x times x, so the degree is 3. So it's odd. Is the leading coefficient positive or negative?
Positive.
It's greater than 0, positive. Okay, what are the zeros? Negative 2, 1, 3. Okay, what is the y-intercept? Well, again, the constant term has to be the product of all the constant terms, right? So it's got to be 3 times negative 1 times 2 times 0.25. So negative 3 times negative 1 times 2 times 0.25. What is it? 1.5. Right? I mean, 2 times 3 is 6. Divided by 4, 1.5. So those are all the points. We could put them on. So we've got, what did we say about the end behavior? It's the same, right? Because it's an odd degree polynomial, the leading coefficient is positive, so it's going to go off in that direction and that direction. It's got a 0 here and here and here. Any of those have that characteristic tangent to the x-axis? Right? What are the exponents on all the factors? 1. So that means it passes through, which makes sense. And now we said the y-intercept is 1.5. So with those points, we should be able to sketch a graph. How about that? Okay, next. So you copied this one as part of the extra credit homework. The turning points of the graph, the turning point of a parabola is the vertex. The turning point of a cubic are these 2 points right there. Now, the turning points of the graph are at the least what they would call local maximum or local minimum. I mean, if you look at that, the vertex of a parabola, that is the absolute minimum on the graph, right? It doesn't go any lower than that at all, right? That is an absolute minimum. But if you look at that point on this cubic, it's not the minimum on the graph because the graph goes infinitely down. So there is a lesser point. But that's called a local minimum because it is the least value in its vicinity. It actually goes up on either side of the turning point. So that is a local minimum. Just like this one here, that is a local maximum. Right. Obviously, the graph goes higher, but in that area, that's as high as it goes. Again, if you go back to the idea of a tangent line, actually these local maximum and minimum for all those points, you could draw a tangent line to it, and that tangent line would be a horizontal line. Okay. And when you get to calculus, you spend about the first half of the course doing just that, trying to find where are all these places where the graph changes direction, where the slope of the tangent line equals 0. It's called differentiation. So for this stuff we're going to do here, I'm putting it in the calculator. The problems in the book for the homework, they're showing you a graph. So you don't actually have to graph anything, not like we did before. They just want you to look at the graph and identify, what are the x-intercepts, what are the y-intercepts, and what are the turning points. Okay, so let's, on this graph right here, understand it's not the easiest to count all these little hash marks there, but what does it look like the x-intercept is? Okay, it looks like the x-intercept is -1. X-int. What does it look like the y-intercept is, approximately? Well, actually, you can look at the equation and tell what the y-intercept is. Yeah, the y-intercept is 6. Okay, how many turning points does it have? Okay, it's got one there at 6, it looks like, and it's got another one there. So the one on top there, that's 0, 6. And we just have to estimate this one here. How do you want to estimate that one as a turning point? 2, 2. Okay, that sounds good. 2, 2. Okay, that's all it's asking us to do. Just identify those things. Now, I want to add something else to it. Increasing and decreasing. Okay, let's state the intervals of increasing and decreasing. Okay, what is the graph doing from the extreme left side of the graph until it gets to the first turning point? It's increasing. It's going up like that. So we would say that it has an interval of increasing. The interval of increasing goes from -infinity to the x-coordinate of the first turning point, which is 0. Okay, now what is it doing in between the two turning points? It's decreasing. So how can we state that interval? It's starting at 0 and it's going to 2. And that's the x-coordinate of 2. Okay, then what is it doing from the second turning point until the end of the graph? It's increasing, and so how could I say that interval? 2 to infinity. That's it. So once you know the turning points, then you can define what are your intervals of increasing and decreasing. And I think there is like an SOL question that they'll put on where they just give you the equation, and then you're supposed to graph it in the calculator and then make that kind of an estimate. Where's the intervals of increasing and decreasing? And the truth, if it's a parabola, we could actually calculate it, right? But if it's not a parabola, we can't. You need calculus for that. Or you could use the calculator to do that. The calculator has a way to find minimum and maximum points. If you go in the calculator, go second trace, and you'll see minimum and maximum in there. But it's not really required for us to do that here. Okay? Yeah. Sure. Have at it. Okay? So here's another one. So what is the degree of this polynomial? Fourth degree. It's a quartic, right? It says it's a positive leading coefficient, so it should open up, and it looks like it's opening up. We can see that there's turning points here and here, and then it looks like it goes off the screen down here. You know, I actually calculated it, and it was about 4, negative 43. I let the calculator find it for me. You can zoom out on the calculator, but then everything else gets really small too. So I did find that one point. Okay, so now based on that, let's identify the x-intercepts, the y-intercept, the local maximum and minimums. Okay, how many x-intercepts do we see? 4, right? So x-ints. And let's estimate. Maybe negative 1. How about, it's not 0. How come? 1/2? Okay, let's call it a half. How about the next one? 2 is good. Close enough for government work, as they say. 1, 2, 3, 4. Maybe the last one is 5. Looks pretty good. What is the y-intercept? Negative 3. The constant term, right? Okay, and then let's estimate the turning points. The first one there, what would you say that one is? How about negative 1/2? And how far down does it seem like it's going? 7. That'll works for me. Okay, how about this turning point? Estimate. 1. Not as far up as the other one was down, so 5-ish. 5-ish. And then I've already labeled that one there. Okay, so let's put the intervals of increasing and decreasing. Increasing, decrease. So what's it doing from the extreme left side of the graph until the first turning point? It's going down, right? This part of the graph is going down. So how would I say that interval? Negative infinity to negative 1/2. Okay, then it's going up. How do I state that interval? Negative 1/2 to positive 1, right? The x-coordinate of the next turning point. Okay, then it's going down again. What will that be? It's starting at this turning point where the x-coordinate is 1, and it's stopping at 4. And this last interval starts at 4 and goes to infinity. Right? Those aren't points, right? Those are intervals. Interval notation. So do that, and you don't have to do the increasing and decreasing. Just say where are the x-intercepts, where are the y-intercepts, local minimums, local maximums. Is that right? So you have to use your calculator. Enter it in the calculator, see if you can come up with the graph. And do you know how to raise to the third power, for example? Does anybody need help with that? You guys say it. So remember, if you want to raise something to a power, you use this little caret key on the right side. Caret or hat, whatever you want to call it. That's how you raise something to a power other than squared, right? If you want squared, you've got a squared button on the left side. But if you want any other exponent, you should go over here and hit that key. Just remember, when you use that key, it puts you up in the exponent, and it doesn't take you out until you right arrow out of it. So make sure you don't just like put everything in the exponent, then you'll have to redo it. Right? You should have a graph that looks something like that. So what did you estimate for the x-intercept? -3. What did you say for the y-intercept?
2.
It's obviously 2, right? And then these two turning points, the -2, 4, okay. 1/2, 2, okay. 1/2, comma, 2. Close enough. Okay, try that one. So what did you estimate to be the x-intercepts? -3, 1.5. Okay, what did you estimate to be the turning points? Oh, what is the y-intercept? Right, that's y-int. Okay, and what are the turning points? This one is -3. Who did you say, 9 or 10? -9. Okay, what about this one on top? What'd you say? -1? -4? Okay, what about this one? 1, -7? Looks about right, okay. So, based on that, what is the range? Greater than or equal to -9, right? -9 is the lowest point on the graph, so the range would be y greater than or equal to -9, if that's the right point. So that's it. And that's the homework. And like I say, I mean, you don't have to do the increasing and decreasing. There's no questions about domain and range. But you do have to identify the turning points, which they call the local maximum and local minimum.